Hi everyone, and welcome to this episode of Keipert Labs. In today's video we're going to be discussing energy efficiency. So what is energy efficiency? Thinking about the law of conservation of energy, one of the fundamental scientific principles relating to this. Looking at energy loss in a given scenario and how we can visualize that using something called a Sankey diagram, as well as then how can we calculate energy efficiency and ways to maximize energy efficiency. So let's start at the top. What do we mean by energy efficiency? Well, ultimately, we're thinking about how much useful energy is being transferred in a situation. So you're putting a set amount of energy in, how much are you getting out? And more specifically, how much are you getting out in the form that you are after? Okay, because what we'll see in a moment is that all the energy that goes in does ultimately come out, but not necessarily in the way that you want. And so we want to be using energy as efficiently as possible in our particular process, in our particular scenario, whether it's a machine, whether it's generating electricity or pumping water, or whether it's, looking at how the best kind of solar panels to get to power your home or your hot water system. Okay, so how much of that energy is being used for its intended purpose? And so the idea that kind of relates to this is what we call the law of conservation of energy. That is to say, energy cannot be created or destroyed, it just changes forms. Okay, so the different types of energy that we've been looking at in the past, like kinetic, gravitational potential, chemical potential, all of those, we're saying that in a particular situation that all the energy that was there at the start is there at the end in some form. Now, it may be in the same form but transferred to a different place, or it may be in a different form within the same object or a different one. Okay, this applies a bit more generally than that. Ultimately, this is also known as the first law of thermodynamics. So in our understanding of the universe, that we describe some fundamental laws about how energy relates to how things work, and so we call these the laws of thermodynamics, and this is kind of the first and one of the most fundamental ones. Okay, and so one of the things to keep in mind here is that this applies to a closed system. So we use this terminology of a system to kind of represent all of the things that we are relating to. Now, we can define that really, really narrowly to a set of particles at the atomic level, or we can be talking about the Earth and the Moon together, or we can be talking about a solar system or the universe as a whole thing. It's a matter of scale and perspective as to what we consider to be the system. And so we're saying, all right, well, when we're in a situation where that's closed, all of the energy is going to remain in that form. Remain in there in some form. So pardon my lack of clarity there. But the reality is that it's impossible to be 100% energy efficient. One of the other fundamental laws of how the universe works says that things in the universe tend towards chaos or disorder. That's a paraphrase. So this idea that we can never be 100% energy efficient. We can be as close to that value as we would like, but we can never achieve it completely. There's always some energy loss. Okay, and so that can be through things like friction. So when surfaces are rubbing together, then some of that energy is lost in that rubbing. Like a box sliding on the ground, it's lost in the form of air resistance or air drag. For a car that's driving, or a plane that's flying, or a helicopter. Okay, that some of that energy involved in the air that's moving past. That's where some of that loss comes in. It's also in the form of heat or light or sound, things in like a car engine, that we want to transfer as much energy to the wheels as possible to make them turn, but that as the engine works, it makes a noise. Some engines, it's very loud, that produces an awful lot of heat, so the car has to be set up to try and cool it down. When things get particularly hot, they can also give off light. Or other circumstances can give off energy in the form of light as well. And so, they're not the only types, but there's some common ways that energy can be lost from a system. We think about taking a ball and dropping it, and it hits the ground, and if it was 100% energy efficient, then it would resume up to the height that we dropped it. We know that it doesn't do that, and that depending on the type of ball, that they make it only a proportion of the way, so that you drop the ball and there's a sound. There's also, you may or not realize it, but it's also heat as well. The ground gets a tiny bit warmer as from that impact. Okay, there are always energy gets lost. And so one way that we can kind of keep track of where the energy is going and how much is being lost is with a representation called a Sankey diagram. Now, these don't only ever occur in terms of energy. They can be also just thinking about amounts of stuff that then get lost or get diverted at different points. But we focus on them in terms of energy. So saying, all right, so we have a certain amount of energy that is going in, that's being supplied to a system, that some of that energy is continuing on in the form of light, and that some of that, the rest of that energy is continuing as being lost, so the arrow pointing down, in the form of heat energy. And also, so that the width of the lines, or the arrows that we draw, represents the amount. You can see that only out of 100 joules going in, only 10 joules of energy is being used as light, whereas 90 joules is being lost as heat. So this arrow is narrow, and this arrow is much wider. So they're proportional to that, to give us a sense of the size there. So the different energy types and the direction. So they're labelled accordingly with amounts. Okay, so the arrow direction gives us useful information to show this is how much is useful energy, and this is wasted energy. Okay, so how do we calculate how energy efficient something is? Well, if we have some data about how much energy is being used and how much energy is being lost, let's turn that into a percentage figure so that we can translate that across lots of different scenarios. So we use this equation here. We say that the energy efficiency is equal to the useful energy transferred in joules divided by the energy that was supplied, also in joules, and then times that by 100 to get a percentage value. Okay, so I'll show you an example now. So let's say we have a modern or energy-saving kind of light bulb rather than an old-fashioned incandescent one that produces 75 joules of light energy for every 100 joules of electrical energy. So we have 100 joules of electrical energy going in, 75 joules of it is continuing on as light, and only 25 joules is being lost in the form of heat. So this is much more efficient. Even just looking at the diagram, you can see that there's much more energy being used as light here than in the previous example, which was for an old-fashioned globe. So we have our 75 joules of useful energy divided by the 100 joules energy supplied times 100 gives us 75%. So we would say that this light globe is 75% energy efficient. So that means that if I put in 200 joules, or I put in 2,000 joules, or put in 150,000 joules, that I can work out how much energy is going to be given off in the form of light, regardless of how little or how much I'm actually putting in. I've got a figure that translates across. Okay, so now let's have a quick think about how we can maximize energy efficiency. So in situations where we really want it to be as efficient as possible, what are things that we can do that will help that to occur? Okay, so one thing we can do is we can swap out older, less efficient technologies for newer ones. Okay, so we can generate electricity in different ways, for example, and as we research and develop more efficient technologies, that they can be better. Okay, so we can make a better choice there from the outset. Different types of solar panels, for example. Okay, and things that have moving parts, that we can use lubrication. So this is, really critical in a car engine, that you have oil that you put into it that helps the moving parts as they slide past each other. Because they're lubricated, it minimizes friction. So they move more easily, less energy is lost in the form of heat, and it also reduces wear and tear, so the parts break less often because of this lubrication. If you run out of oil, it's catastrophic for your engine because it runs a little bit and it will break apart. Okay, and likewise, if heat is an issue of energy loss in the system, that we can minimize heat transfer. So in your house, for example, you can use insulation. These are pink bats that you can put in your walls and your ceiling and perhaps under your floor in the right circumstances that can minimize heat transfer. That can be heat transfer in on a summer's day, so it keeps it cool inside, and you need to use less energy to cool your house with an air conditioner or fans. Or likewise, it can also stop heat loss when it's warm inside in winter, so that you don't need to spend as much energy to heat your home. So, this is just one example of that, but saying that minimizing heat loss means that we are much more energy efficient. Okay, so we looked at what we mean by energy efficiency in terms of how much useful energy is transferred compared with how much we started with. We looked at the fundamental scientific idea of the law of conservation of energy, also known as the first law of thermodynamics. We looked at different ways that energy can be lost from a system and how we can represent that visually with a Sankey diagram, and then looked at how we can make a calculation involving energy efficiency and different techniques we can use to maximize the efficiency of our system. Thanks very much for watching. Bye for now.